Hello, Science 20s. Today we're going to apply all of our knowledge from oxidation and reduction into a real life example. We are going to look at something called voltaic cells. Now, the large category for this is called electrochemical cells, but we're going to only look at half of that today. We're going to look at this piece right here. We're going to look at those reactions that are spontaneous, those reactions that produce electricity by being spontaneous. The reaction just naturally goes, which means every example we're going to look at today is going to be a voltaic cell. There's the opposite of this, which means the reaction is non-spontaneous, and we need to provide electricity to get the chemical reaction to take place. And that is going to be in a future video called an electrolytic cell. Everything we do today is going to be spontaneous, meaning downhill. It will automatically produce electricity. We can think of this as a perfect example of a battery. Batteries have chemicals inside and they naturally produce electricity. So let's move on to the next slide. So when we use the word voltaic device, this is a device that continuously converts chemical energy, the chemicals inside, let's say a battery, into electrical energy, something I can use to power my remote control, power my electrical little car. Okay. The key to this is it's got to be spontaneous. OA is above RA, it goes downhill. This means we're going to have a continuous transfer of electrons. Now, some of you in elementary school might have done, let's say, a lemon clock or a potato clock or a tomato clock, and you saw that. As long as you have two different types of metals and one solution that conducts electricity, like a lemon or a potato or a tomato, you can actually have produce electricity enough to maybe light up an LED light, as in the example on this picture right here. Now, what I want to do is I want to show you how to build a battery, and we're going to go step by step by step. In class, this would have taken quite a while, so this is going to for sure be a multi-step video, and I'm going to go as slow as we need to go so that you still understand what's going on. So for this basic voltaic cell, and I want you to at all times think of it like we're looking at a battery. So we know on a battery, there's two sides to a battery. We know there's labeled positive side and a negative side. And so you've seen many batteries before. Well, in a voltaic cell, in a battery, every battery needs the same three parts. It needs two electrodes, an electrode on one side of the battery and an electrode on the other side. And it also needs those electrodes sitting in solutions, solutions that would conduct electricity. I believe you know the term already, electrolyte. So it's got to be able to conduct electricity. So in the example I have on my screen, I have a copper electrode, piece of copper, in a copper 2 solution. Copper 2 nitrate, copper 2 sulfate. Again, if we remember, the nitrate and the sulfate, they're not going to matter. They're not the thing gaining or losing electrons. They're spectator ions, so we're going to ignore them for right now. In the other container, we have the other electrode. In this case, it's a zinc electrode. It's a piece of zinc metal. And we're going to put it inside zinc solution. Again, zinc nitrate, zinc sulfate solution. The sulfate and the nitrate doesn't matter because it's a spectator ion. The key to this is, and I wrote a note here, copper goes in the copper solution, zinc goes in the zinc solution. That part is very, very important. That is honestly the starting block of this. If you get that mixed up, your battery is not going to work the way you want it to. Now, the second thing we have to understand is, although there are two electrodes on a battery, you'll remember that one side is always positive, one side is always negative. If you've ever gotten a toy and put the batteries in too quickly and your toy still doesn't work, most of the time it's because your batteries are in backwards. So you pop them out and you actually pay attention to the little picture on it and goes, oh yeah, this positive side's got to go on this side. That is really critical. Well, the two sides of a battery are called the cathode and the anode. And while I teach about all the parts of the battery, there are five what I like to call cheesy Mr. Kemp rules you need to know. Cheesy Mr. Kemp rule number one in a battery: cathodes are always positive, anodes are always negative. Now, the reason I call this a cheesy Mr. Kemp rule is When I think of cathodes, I see the word cats. And we all know how much I love cats. Cats are fuzzy. They make Mr. Kemp smile. That puts me in a really positive mood. Oh, cats are amazing. So, cathode is the positive electrode. Anodes, on the other hand, if you're anti something, you're against it. Anodes, I always say ants show up at the picnic. They steal my picnic basket full of sandwiches. That really bothers me. That pisses me off. That puts me in a negative mood. So anodes are negative. Cathodes, fuzzy cats, they're positive. That's how I remember it. Cheesy rule number one. The second thing you have to remember about cathodes are not only are cathodes positive, but cathodes is where we have the reduction half reaction occurring. So this is where the reduction half reaction, right? Gaining electrons occurs. So if I take a look, my half reaction is written so that the copper half reaction for the copper beaker is written so my electrons are on the left-hand side for gaining electrons. Gaining. The anode is always where oxidation half reaction occurs. And so my zinc half reaction, I'm going to write it so that it's losing electrons. Losing electrons, oxidation. Now, the reason I know this is true is, if you remember, we're using copper, zinc, and their solutions. So I'm going to jump ahead one slide. And what I'm going to do is I'm going to come along and grab my pen here, and I'm just going to make some circles. So remember, we are looking at copper, and we are looking at zinc solutions. We are also looking at copper solid, and we're looking at zinc solid. So those are my four substances. I always find them first. Now remember on this chart, since when I read from left to right across all these are all reduction half reactions. Reduction goes hand in hand with oxidizing agents. And so at the top of this chart, this is my strongest oxidizing agent. Bottom right-hand corner, this is my strongest reducing agent. And so what I'm going to do is I'm going to start at the top and I'm going to go down until I hit my first substance. Well, my first substance is Cu2 positive. That means it's the strongest oxidizing agent that I have. So I'm also going to put my finger down here and I'm going to go up from the bottom. I'm going to find the strongest reducing agent that we have, and that is going to be solid zinc. Now you'll notice if I pick my strongest oxidizing agent and my strongest reducing agent, the one thing I want you to notice is this will always be spontaneous. Because remember, this is a battery. When I go to use this, the chemicals in here will automatically cause there to be electricity. So this has to be a spontaneous reaction. There is no purpose grabbing a battery if it doesn't do anything. So it's got to be a downhill reaction. It's got to work. So when I go to look at this reaction, my SOA, remember SOA goes with reduction. My reduction half reaction, I'm going to copy this whole half reaction right here, and I'm going to copy it from left to right. Cu2 positive plus 2 electrons goes to Cu solid. My zinc reaction, again, right, we're starting down here. This is my strongest reducing agent. So I'm going to use this reaction right here. But the difference when I use it this time is I'm going to copy it from right to left. So I have zinc going to Zn2 positive plus 2 electrons. So if I take that with me to the other page, and again, I'm just going to go back one page here. So I'm going to erase that, and we're going to go back one page. You will see that those are the two reactions that I have. I have the reduction half reaction for copper, and I have the oxidation half reaction for zinc. Now, the question is, how do I know that the reduction half reaction goes with cathode? Well, that's Mr. Kemp's cheesy rule number 2. So cheesy rule number 1, cats are positive, they're fuzzy, they make Mr. Kemp smile, that puts him in a positive mood. Cheesy rule number 2, ants show up at my picnic, steal my picnic basket full of sandwiches, that makes me angry and negative. Anodes are negative. Well, I also know that cathode always occurs on the side with reduction because consonant, consonant. I always know that oxidation occurs where there's the anode because vowel, vowel. So Anode always occurs at oxidation. Cheesy rule number 2, vowel, vowel. Cathode always occurs at reduction. Cheesy rule number 2, consonant, consonant. So that's how I'm always going to know. Vowel, vowel, consonant, consonant. They pair up together. Well, let's take a look at this again. Here's my rule. Cathode always pairs with reduction consonants. Anode always pairs with oxidation vowels. Make sure you write it down. Now, once we have built this and we figured out who's the cathode, who's the anode, who's reduction, who's oxidation, we also have to add in a wire to connect these two, right? We have to be able to connect these two reactions. This is where electrons are going to flow. Now, I want us to remember this. Electricity is the flow of electrons. In grade 9, when we talked about electricity, we said, hey, if you ever stuck like a paper clip or a fork in the wall socket, you got a zap. And that was a pile of little E minuses coming out of the wall using you to go through because you conduct electricity. So it's E minus, E minus, E minus. Well, we're going to have this movement again, moving in from one electrode to another electrode. These electrons have to flow through something. And in our picture, they're going to flow through a wire. Now, we put a voltmeter in here because voltmeters measure voltage, and that will, when the needle moves on a voltmeter, that will let me know that, oh my goodness, we now have a voltage, which means, hey, we made a battery. Now, the key to this is, here's cheesy rule of Mr. Kemp number 3. Cheesy rule number 3 says electricity is smart. Electricity only flows alphabetically. Electrons flow always from anode to cathode. So here is my oh, gotta go back. Didn't have my pen. Wait. Okay, get my pen now. So here is my anode, and the electrons always flow through the wire alphabetically from anode to cathode, from A to C. So my electrons are flowing this way through the voltmeter. Now, if we see the little needle move, and now it has a voltage, we know we made a battery. However, in this case currently, we don't have a battery. Because if you remember back to grade 9, in order for us to have a battery, we have to have a complete circuit, right? So if I draw a quick little battery here using our symbols, we need a complete circuit. I'm going to put a little light bulb in here for this light to, hey, it's going to turn on. However, we don't have that. We have our electrons going from here to here, but now they're stuck. It's kind of like, if you think about it, we have a break in our system right here, right? We have this switch and it's not closed. That means my light is not going to light. My light is now not turned on. My light is dead. So we have to figure out, how can I complete this circuit? Right now I have all the electrons going from the anode to the cathode, but they're stopping at the cathode. Well, that's because we have, again, another rule. So the other rule is, to complete this circuit, we're going to throw in something called a salt bridge. A salt bridge is a tube with a solution in it. And the key to the solution is the solution has to be able to conduct electricity. It's got to contain an electrolyte, something that conducts electricity, something that has ions. So since I called it a salt bridge, I'm going to put salt in here. Na positive, Cl minus ions. We don't care what you put in as long as it conducts electricity. So it's got to be either an acid, a base, or an ionic compound. I'm going to pause here in the video, and then we're going to start part 2.